everyone, and welcome again to Edge Enhancement lecture. My name is Olivier Rukundo. I am project researcher at the University of Eastern Finland. In the previous lecture, I explained how convolution works for edge enhancement in the spatial domain. And for demonstration purposes, I used two CT images and two TM images. I also used two convolution kernels, horizontal and vertical edge kernels. And in each image case, I presented the result using horizontal and vertical edge kernels with and without one at the central coefficient or at the central pixel of the kernel. In today's lecture, I'm going to show or talk in general about key steps needed for the implementation of filters in the frequency domain with an example of enhancement. I'm also going to use the previous lecture images and kernels to produce similar edge enhancement effects in the frequency domain via discrete Fourier transform. Before I start, I would like to remind in brief what the frequency domain is. Considering this CT image with one side length equal to m and the other equal to n, and let f of x, y denote this m by m image with x that varies from 0 to m minus 1 and y that varies from 0 to n minus 1. The two-dimensional discrete Fourier transform of f, denoted by f of u, v, is given by this equation. Now, answering the above question, here the frequency domain is simply the coordinate system spanned by the discrete Fourier transform of the input image f of u, v, with u and v as frequency variables. This is analogous to spatial domain, which is the coordinate system spanned by input image function f of x, y, with x and y as spatial variables. Note that the rectangular region defined by u that varies from 0 to n minus 1 and v that varies from 0 to n minus 1 is often referred to as frequency rectangle, and it is of the same size as the input image. Also note that the inverse discrete Fourier transform is given by this equation. Also, I would like to remind you that discrete Fourier transform offers considerable flexibility in the design and implementation of filtering solutions in areas such as image enhancement, image restoration, image data compression, and a host of other applications of practical interest. Of course, it's also possible to combine spatial and frequency processing to yield results superior to using either type of processing alone. But of course, this is not covered in today's lecture. Now, referring to previous lecture on edge enhancement, when an output image is obtained by convolving an input image with the kernel, as shown here, the convolution theorem states that the Fourier transform is given by G of U comma V, that is equal to the Fourier transform of the kernel times the Fourier transform of input image. Therefore, enhancement can be achieved directly in the frequency domain by a pixel-by-pixel multiplication between the discrete Fourier transform of the input image and the discrete Fourier transform of the kernel, and forming the enhanced image with the inverse Fourier transform of the product, or simply by following these three key steps. Here it's important to note that, of course, depending on the aim, it's possible to suppress noise or smooth image, for example, by eliminating high frequency component of the discrete Fourier transform of input image, or enhance edges by eliminating its low frequency component. More details can be found in the books such as Digital Image Processing with MATLAB and or Handbook of Medical Image Processing and Analysis. Now, let's use the previous lecture images and convolutional kernels to produce similar edge enhancement effect in the frequency domain using discrete Fourier transform. Now let's start with the horizontal edge kernel and see the image. And and here one is not added to the central pixel of the kernel, and the output image obtained using the discrete Fourier transform looks the same way as the output image obtained using the convolution of input kernel. So here it's easy to notice that. And then, of course, this is input image, and then this output image. And when we add one to the central pixel of the kernel, we get the output image from the discrete Fourier transform that also looks similar to the output image obtained using the convolution of input kernel. So in this case, the images also look similar. So now let's use the vertical edge kernel. And here we don't add one at the central coefficient. Again, the images look the same way. They are similar. The output image from the discrete Fourier transform and the output image from the convolution of input kernel, they look the same way. And in this vertical edge, when we also add one to the central coefficient of the kernel, we get the output image from the discrete Fourier transform that also looks like the output image from the convolution of input kernel. So similar effects can be noticed in two cases. So now let's use the transmission electron microscope image, and we can see that the same effect happened. So we have the images from both techniques that looks the same way, just like in the previous examples. And if you add 1 to the central coefficient of this horizontal kernel, so the output image looks the same way also, just like in the previous cases, except that here we are using a different image. Let's try again with the vertical edge kernel. Without 1 added to the central coefficient, of course. So the effects remain the same. The images from the image from the discrete Fourier transform look like the image from the convolution of input kernel. And of course, when we put 1 to the central coefficient, we obtain images that look the same way, as you can see here. And this is the end, but something I would like to experiment is that, unlike in the previous lecture, here we didn't use the sum of original and edge enhanced image like in the previous case. So this is a kind of exception in this demonstration provided in this lecture. Now, this is the end of today's lecture. Thank you.